Radiation. It's a word that often sparks concern, but what exactly is it? Simply put, radiation is the emission and propagation of energy through space or a medium. We generally categorize it into two forms: electromagnetic radiation, which includes X-rays and gamma rays, and particle radiation, such as alpha and beta particles or neutrons. The key distinction lies in whether radiation is ionizing. Ionizing radiation carries enough energy to liberate electrons from atoms, creating ions. Non-ionizing radiation, like visible light or microwaves, lacks the energy to break these atomic bonds. There are three primary types of ionizing radiation we encounter: alpha, beta, and gamma. Each has a distinct mass, charge, and energy loss mechanism. Alpha radiation consists of heavy, positively charged helium, 4 nuclei. They have high ionizing power. A classic example is the alpha decay of radium-226 into radon. Beta radiation involves high-speed electrons or positrons. These particles are much smaller and travel at relativistic speeds. Positrons are particularly interesting as they are antimatter counterparts that can undergo annihilation, releasing gamma photons. Gamma radiation consists of high-energy photons with no mass or charge. Because they are pure energy, they follow the Beer-Lambert law, meaning their intensity decreases exponentially as they penetrate deeper into matter. When these photons hit an atom, they interact in specific ways. In the photoelectric effect, a photon is completely absorbed and its energy is used to eject a photoelectron. This is the dominant process at lower energy levels. At intermediate energies, Compton scattering takes over. Here, a photon strikes an electron and scatters, losing some energy and changing its wavelength. Which process dominates depends heavily on the photon's energy and the atomic number of the material it's passing through. Penetration isn't just about the material, it depends on the particle's kinetic energy. The Bethe-Bloch equation describes how charged particles lose energy as they travel. For heavy particles like protons, we see the Bragg peak. Energy deposition actually increases as the particle slows down, peaking sharply at the end of its range. This principle is vital in modern proton therapy to treat tumors while sparing healthy tissue. Radiation is all around us. About 80% of our average exposure comes from natural sources like cosmic rays, terrestrial minerals, and even the potassium in our own bodies. The remaining 20% comes from artificial sources, primarily medical diagnostics like CT scans, as well as industrial uses and nuclear reactors. In summary, whether it's an alpha particle or a gamma wave, understanding ionizing radiation is essential for medicine, safety, and the future of energy.